not yet. Once we hit the buttons here, if you want the record to show, now you can say, let the record show, and it'll show it. Anyway, all right. So we're back to, I'm not sure what we're back to. I can see myself here on one screen, but I see a taco or something on another screen. What is that? I don't, it's a rabbit or something. Anyway, it's real small for me right now. So, okay, now this is not as good as that was, what Dalton had. Now, by the way, one question, just personal, but not personal, to Natalie. Did you get things worked out on what you wrote me? I didn't respond to you because it looked to me like you got into the system.
Yes, I did.
Okay. I apologize for not responding. I kind of was going to, and I forgot about it. And the next time I looked, you were enrolled. So anyway, no big deal. I just wanted to make sure I told you that, so at least you might forgive me in time, you know, not right away. Okay. All right. I want to go back to these notes because I think that those are, they're out there for us. And now I'm going to kind of sort of go back here. I'm sorry, I was up several pages here. And get back to where we were kind of talking about. Yesterday, we were kind of around this page, 10, 11, 12 sort of page, where we were talking about several systems that you're very familiar with, but you probably haven't had this kind of instruction. Basically, when, and my wife says I say basically too much, so you might tell me that when I say that and tell me I'm saying it again. What we're doing is looking at systems which involve a set and things we do with the set. Now, we could just take sets themselves and we could define the concepts of union of the sets and intersections of the sets and complements of the sets, things like that. That would be one way to combine sets. But what we're talking about here is not just combining sets, but we're talking about what the sets consist of and combining the elements of the sets, not combining the sets themselves necessarily. And so when you think about counting, for example, there's a certain arithmetic that involves counting. And in that process, although what you've learned is you've learned the real number system, and when you're talking about the whole numbers, you're thinking of it as a subset of the real numbers. Well, I'm going the other way. I'm saying, suppose we start out with a set of whole numbers and we don't even maybe know there's other numbers besides them. So we restrict ourselves to just whole numbers. Well, that actually restricts what we can do because we can add them together and we can multiply them together, but we have to be very careful if we try to subtract or divide. And you know, if you've ever had like 5 pieces of pizza and 10 people at a party, that you got a problem if people want to eat pizza because you don't have enough to go around. And so you can't solve the problem of giving 5 pieces of pizza to 10 people, not if each person gets a single piece. All right, it just doesn't work. And so when you're dealing with the limited idea of just numbers that you count with, including 0, you're limited on what the operations you put on them of addition and multiplication, what you can do. For example, if I say 6 is divisible by 2, everybody would agree with that, I think. But that's not an arithmetic problem. That's a true-false question. 6 is divisible by 2, the answer is yes. If somebody says, why? What you probably would say is, well, because 2 times 3 is 6. But you see, no one asks you to divide 6 by 2. They just ask you if 6 is divisible by 2. The fact that you can get an answer is why you say yes. But it's not an arithmetic problem. I mean, it's not a division problem, it's actually a multiplication problem because you justify what you say by multiplying. And if I said, what's 7 minus 2? You'd say 5. And if I say why, you'd say, well, because 5 plus 2 is 7. So when you only have the concept of whole numbers, you do not have a full-blown subtraction. You can only take differences, and differences mean that the thing you are starting with is bigger than the thing you are getting rid of. So a difference is, you can take a difference of 7 and 5. That would be 7 minus 5. We use a minus, but not as a full-blown operation. It's a difference. You do not subtract if you're limited to whole numbers, because you can't say 2 minus 5. There is no answer to that. Okay, so now suppose we were in a world where we only understood whole numbers. That's all we know. And we wanted to trade with people. And so you want to buy and sell, you basically, or to put another way, suppose you want to have bank accounts and you're trying to figure out how in the world can we talk about being overdrawn? How can you talk about spending more money than you have? Things like that. And that requires a different system called integers. But if I do not have the concept of integers, how can I construct it? How can I create a system that I do not have in my world yet? Okay, that's the problem. Well, here's the way we do it. And I'm going to get off of this page I'm on here and get back to something that I can write on. So just a moment. Suppose you're now going to see a white sheet here. Suppose I take my set of whole numbers, I'm going to call that W. And suppose I make a relation. And so I'm going to take some whole numbers, A, B, C, and D. These are whole numbers. Okay, 4 whole numbers. And I'm going to pair them up. I'm going to put pair AB together, I'm put pair CD together, and I'm going to make up a relationship. Now, sometimes when we talk about relationship, we put the relationship between the things we're relating. Like if I said so-and-so is married to so-and-so, the relationship that you're talking about is between the two things you're talking about. So I'm saying AB, when I write it this way, I'm saying AB is related to, okay, this is how I would read it. AB is related to CD if and only if, and I abbreviate that with IFF, A plus D is B plus C. Suppose I tell you we're going to deal with this relationship between pairs of whole numbers, okay? Then the question is, well, first of all, you can prove, all right, we can prove that R is an equivalence relation. I don't want to waste time doing that right now, but we can prove that. So if you take my word test for a minute, you'll see where I'm going with this in a moment. You can verify that this is one of these equivalence relations that we mentioned yesterday. So given that it is, then that means each, like AB is related to AB. Now you can prove that real easily. If C and D are A and B, then what do you have here? You have A plus B and you have A plus B over here. So if C is A and B is D, you'll see that this is true. So things are related to themselves and so on. Anyway, it's an equivalence relation. Now, what's an equivalence relation do? It divides all these pairs into sort of what I call wastebaskets. In other words, I'll have some ordered pairs, like let's take the ordered pair 3, 1. That'll be in some wastebasket. The ordered pair 7, 5 will be in some other wastebasket. And maybe I'll have an ordered pair 1, 1, 6. That'll be in some wastebasket. Now, when I say wastebaskets, I'm just thinking about like if I worked in an industry where I'm picking fruit or something, and I'd pitch some fruit in one barrel and some other fruit in another barrel based on some kind of criteria. Maybe something's rotten, or Maybe something's not ripe yet or something, but I'm taking my objects and I'm making some decision as to which place I put them. Well, the place I'm putting them here would be, I put two in the same place if this is true about them. A plus D is B plus C. So I contend that if I would take like, let's say 12, 10, I contend that 12, 10 would be in the same place as 3, 1. Why is that? Because 3 plus 10 is the same as 12 plus 1. Now, does everybody understand? To test whether or not two things are in the same equivalence class, we take the first thing and the fourth thing and the second thing and the third thing and see if we get the same answer. Okay? Anybody confused by that? Well, what about 7, 5? Would 7, 5 be in the same wastebasket or a different wastebasket?
Same.
To be in the same wastebasket, 3 plus 5 would have to be 7 plus 1. It is. 12 plus 5 would have to be 10 plus 7, you see? So this is really the same wastebasket, same equivalence class. What about this one? Is 7 plus 6 the same as 5 plus 1?
No, they are different
This
baskets.
is a different equivalence class than this one was. Okay? Now, I hope you can see that each wastebasket is going to have lots of pairs, millions of them, billions of them, trillions of them, whatever. Right? Now, so I got a bunch of wastebaskets. Like I have a 1-6 wastebasket. I'm not naming it, but 1-6 is in it. I have another wastebasket over here, or an equivalence class. I just say a wastebasket because some of you think this is nonsense. Anyway, I have 7, 5 and 3, 1 and 12, 10. They're all in the same equivalence class. What humans do is they like to classify. And as soon as I see a few in here, do I see any pattern between what's in here? See, to test them, you're supposed to go up here and try this first plus fourth and second plus third. But what's common between these three?
The difference between the x coordinate and the y coordinate is 2.
Yeah, the first number is 2 bigger than the second number. Once you see that, you can dream up a whole bunch more real fast without testing them. In other words, what humans do is they say, oh, I see a pattern. And once you see a pattern, that's a shortcut. So I'll bet you 4, 2 is in there and 5, 3. And you can test them, but I think you're going to see they are. Okay? Now, what's another thing that would be in 1-6 wastebasket? How about 2, 7, 3, 8, 4, 9, 5, 10, 6, 11, okay? Right? As I said, once I start seeing patterns, I can quickly put more in the same place. All right? Now, what we want to do is we want to name each wastebasket, each equivalence class, so that we can use these things as single objects. In other words, what I'm going to have is a bunch of equivalence classes I'm going to treat as single objects. So I'm not going to be looking at the pairs, I'm going to be looking at the name of the wastebasket or the equivalence class. And I'm going to name this equivalence class positive 2. I'm going to name this equivalence class negative 5. So arithmetically, I would have the following. 3, 1 is a member of positive 2. Because positive 2 is the name of the class, and the pair 3, 1 is a member of the class. Does that make sense? Now, what do you think of if somebody asked you, how do you define integers? you probably say, oh, you got +2 and -5, and you got a bunch of those things. I don't care how you denote them, but I bet you try to start telling me what they look like. Like I got +10, I got -5, and you might use plus and minus because I ask you about integers, and so maybe I'm being very technical. You don't want to just say 3. You probably want to say +3 because that's really what an integer is. Anyway, where is this useful? Well, if you think about this, like if I have $3 and I owe 1, how many dollars do I really have? In other words, if we buy and sell, if the first number is what I owe you and the second number is what you owe me, we can set up commerce. In other words, integers are used in banking, in commerce, because we want to know how much you have compared to how much something else is. What's an overdraft in a bank?
Where you pull more than what you have.
Yeah, and more, and right, exactly. And so if you have, if you owe, if you write a check for $5 and you got 0 in the bank is going to say, hey, you got -5, right? But what I'm trying to get at here is 0.5 to the bank is the same as 1 million. Okay, I'll get enough zeros here. I shouldn't have said 1 million. To the bank, 0.5 is the same as 1 million and 1,000,005. In other words, if you've got $1 million in the bank, but you write a check for 1,000,005, you're in the same place as if you have 0 in the bank and you write a check for 5. Because it's the difference that we're interested in here. And who owes whom depends on whether the difference is positive or negative. But you can't have negative differences. That's why the bank fines you. Now, by the way, it's always funny to me, if you don't have any money in the bank, then they charge you. Where do they expect to get their money? Anyway, and I might tell you, this is not a political statement at all, but some years ago, Donald Trump owed the bank $300 million. Okay. And some news person said, boy, you're in trouble. You owe the bank $300 million. His reply is, I'm not in trouble. The bank is in trouble because I don't have it. And neither does the bank, but it's the bank's money. So they're the one that's hurting. I'm not hurting. And it's an interesting statement, but it's true. If you owe somebody $5, it's your problem. But if you owe somebody $100 million, it's their problem, if you think about it a little bit. Anyway, that was just, to me, an interesting statement that was made about very rich, very big amounts of money. Okay, now, okay, so this may seem like a weird system to you, but we could have named this wastebasket the wastebasket 7.5. In other words, we could have chosen a name for integers that involved 2 numbers. We didn't. We chose instead to put a minus or a plus on what makes the difference between the 2 numbers. Okay, now, but let's try to do something that might interest you. I don't know. How do you think you add 2 wastebaskets together? In other words, suppose I have A and B out of one wastebasket and C and D out of another wastebasket. Now what we do is we do something different for the wastebasket itself. So suppose I name these wastebaskets. I name the wastebasket that's +2. Suppose I might name it 7.5, but I use brackets different or something. So we know we're not talking about the pair, we're talking about the wastebasket. Then I can define this the following way. I just add the first things together and I add the second things together. And I make a new wastebasket. Okay? Now, let's try it. Suppose I want to add +2 and -5. What do you get? You get -3, right? Everybody?
Yeah.
Okay.
Yep.
But will you agree that for some kids, this is a difficult problem? Some people have trouble with these kind of problems.
Yeah.
All right, well, let's take a representative of 2, +2. Let's make it, I don't care, 12, 10. I don't care what we take. And let's take a representative of -5 to be 1, 6. I don't care what we take. And let's fix this up. By the definition, 12 and 1 is 13, 10 and 6 is 16. What wastebasket is this in? 13 and 16.
-3.
-3, and all you're doing is adding whole numbers together and figuring out what it is afterwards. And if you really think about this, this is neat. And it turns out that if you're programming computers, which are totally stupid things, this is how you do it. Because you try to figure out how do you do arithmetic with negatives and positives. You don't have to. You just use pairs. It's much easier. So it turns out that adding integers is easy because all we do is add the assets and we add the liabilities and we figure out what it is afterwards. We figure out who owes who after 2 transactions instead of 1, you see? And I'm hoping that you'll appreciate how easy that is and how easy it is we could teach children this if we used a different system to denote positive and negative. Because there's no subtraction. There's only noticing at the end which is bigger. If the second one's bigger, we say minus. If the first one's bigger, we say plus. And that's easy to figure out. Now, integers were developed to add. The addition property is easy here. How do you multiply 2 integers together? What you guys did is you learned a complicated system that dealt with pluses and minuses. It turns out that you can easily define how to multiply here, but it's more complicated. Integers were not developed to multiply. They were developed to add and subtract. Rational numbers were developed to multiply. So now, what I hope to do is just a short time here. Suppose we now had the integers, but we have never had rational numbers. In other words, suppose I'm one step up. So it turns out we can define a relationship between integers that will give us the set of rational numbers. And the relationship now is if I take 4 integers, and remember that was the letter Z, and I take pairs of them, okay, and I want to relate them, it turns out that the process is A times D is B times C instead. And when we do that, it will turn out, for example, that if I take the pair 2, 4, and I take the pair 3, 6, the pairs, positive, are these related? How do you check they're related? You see if +2 times +6 is the same as +4 times +3.
Dr. Brady, we can't see what you're writing down there.
I'm sorry. Yes, thank you. You see if is +2 times +6 the same as +4 times +3. And the answer is yes. So these are in the same wastebasket. But another thing that's in that wastebasket is +1, +2. What's the relationship of all these things? They're all in the same wastebasket.
2 times.
The second thing is 2 times as big as the first thing, right?
Yep.
Or the first thing is half as big as the second thing. This wastebasket is named 1/2. Now, what's the difference between this new system and the old system? When people named rational numbers, they decided to keep both numbers. So all of you believe that 1/2 and 2/4 and 3/6 are all the same number. Why? Because they're all, the pairs are all in the same wastebasket. These are names for the wastebasket. The names are equal because they refer to the same set, these pairs. But you never learned us stuff about pairs, but what you learned about was the fact that with rational numbers, you need 2 numbers. What you never thought of, I'll bet you before, is with integers, you need 2 numbers also, but people don't represent them with 2 numbers, they represent them with pluses and minuses, and therefore confuse a lot of people that wouldn't be confused if we did it differently. Anyway, so I'm trying to show you here of integers are equivalence classes. Whole numbers are equivalence classes. Practically everything we use in math are equivalence classes. You guys have just never seen them before. And that's because nobody thought you were competent enough or mature enough mathematically to understand that. So I'm hoping you are. And I'm going to go away from that. But I'm hoping you're going to see a reason why, in terms of trying to understand stuff, we define a set, and then we define operations on a set. And what I just did was try to show you some equivalence classes that build one world from another world. Okay? Now, so in playing around like I've been doing, you actually can build up rational numbers. And notice here, rational numbers, what I wrote here is how you add them. Adding rational numbers is complicated. Multiplying rational numbers is easy. And that's because rational numbers were developed for the purpose of multiplying. They weren't developed to add. So when you multiply them, they're easy. When you add them, they're hard. Integers, on the opposite, they were developed to add and subtract. And so it's easy to add and subtract them, and it's difficult to multiply them. But our purpose is not to study all that. I just want to tell you about it. And so what happens is, in the 20th century, is people started classifying stuff like I'm doing now. And then they found out that they could be more abstract. In other words, various systems had things in common. And the common things, it turns out, we start naming. Like when I say A plus B is B plus A, or I say A times B is B times A, except for the operation, I'm saying the same thing. I'm saying A operate B is the same as B operate A. So I can say I have one concept of putting them together that stands both for addition and multiplication. Is called the commutative law. And so people started classifying in the 20th century this stuff, and they came up with this, what you'll find to become, it's very abstract, but kind of a strange thing. So if I take any non-empty set, any collection at all, take a bunch of cows in a field if you want to. I don't care what you take. That'd be kind of silly, but you can do that. Somebody once gave me a coffee cup that said I was outstanding in my field, and they showed a cow out in a field, the cow outstanding in the field. Anyway, if I take a non-empty set and define an associative binary operation on that set, now that's from yesterday, then we call the set together with the operation a group if 2 more things are true. Okay? So you have a binary operation, and you have an identity, and each object has an inverse under the operation. That's called a group. So a group is an associative binary operation on a set that has an identity, and everybody has an inverse under that operation. So it turns out that the whole numbers under addition is not a group because you don't have inverses under addition. But the integers are a group because you have inverses. The integers are not a group under multiplication because you don't have inverses. But the rational numbers are a group because you do. Now, what I haven't mentioned here is also in heavy print here on this page, a commutative group means you have associativity as well. And it's also called an abelian group after the Norwegian Niels Henrik Abel. Sorry, not Abel, Abel. Anyway, so then what you have here on the page is group properties. And I don't have time to, it's 11 minutes after, but you have properties of a group. And what we're talking about here basically is trying to abstract what is common between adding integers and multiplying by rational numbers. What's common when you add functions, for example, because we can add functions. You had Calc 1, we add functions. We multiply functions. Functions are commutative. It turns out that there's an identity function. You've heard that name. And so functions might be a group, okay, under an operation. And it turns out that all the different things you've studied can be classified into these abstract structures. And when you find two things that have the same properties, you don't have to study both of them. You study one and you get the other, you've got the properties for the other one free. Anyway, we have some properties. And I'm going through this now without going through it because we don't need all this now for Calc 2, but we may want to refer to it at times, okay? And the next thing we get is called a ring. A ring is when you have two operations, which we usually call addition and multiplication. And so you can read about that. That's when you have a set with two operations, addition and multiplication, okay? And their properties. Now, there's something called an integral domain. What do you think that's patterned after? And the answer is patterned after the integers. An integral domain is a thing that when you look at it, it looks like you're dealing with integers. You're not, maybe, but it looks like. If you have a group under both addition and multiplication, then you have what's called a field. And it turns out that the rational numbers become a field. It means you can add them, you can multiply them, you have association, you have the associative law, the commutative law, you have identities, you have inverses. So the rational numbers become a field, the real numbers become a field, the complex numbers become a field. And what I'm talking about is what defines algebra. When you talk about algebra, I'm not talking about high school algebra. Algebra is a study of these structures. If you get into graduate school and you take a test on modern algebra, it will be a test about groups, rings, and fields. That's what algebra is about. And polynomials that you studied in high school are an example of a certain structure that is in algebra, okay? So it turns out that an algebra is a structure that you make up that has certain properties. All right, now, once you have a field, what we haven't talked about yet is order, because we think of one number being less than another. So we have an ordered field, and the P here means positive. And again, most of this, I want you to go through it, but you're not going to be tested over it or anything right now. positive numbers. These are the properties of positive numbers. Later, you get less than, and we get the trichotomy law. You remember the trichotomy law? Any two numbers, one's less than the other, or they're equal. There's three different things that can happen. I wrote down the laws of inequality. Okay, and the proofs. Absolute value. Properties of absolute value. Then we get into the Archimedean principle. You may remember what that is. If you take two numbers, you can multiply one by another by a number and get bigger. Take any two numbers, multiples of one will sooner or later get bigger than the other. And then we have sequences, and we haven't studied sequences yet. And that's in Calc 2, so I'm going to skip that. But when you get all that done, one of the things you have built is what's called the real line, which you guys have assumed you've known about since grade school. Okay, so all I've been doing here in an abstract way is reviewing the properties of the real numbers. Because the real numbers have a subset that looks like the whole numbers. They have a subset that looks like the integers. They have a subset that looks like the rational numbers. You've always thought they were, but they just have subsets that look like those systems. And the look like is called an isomorphism. When we can't tell the difference between two systems because they have all the same properties, they're called isomorphic. Iso in Greek means the same, and morphic means has to do with change. And basically you're saying they have the same properties. So anyway, what I'm trying to get to it is 16 after, but this is all the abstract stuff that mathematicians classify stuff with. And I know you're not going to learn it all right now. That's okay. I want to just kind of go through it. What we really want to talk about so we can get to section 2 in the vector spaces. And by the way, I saw that a lot of you, I think 15 of 19 of you yesterday had started and maybe gotten through the first of the exercise sections. Okay. As of yesterday, only 4 people had started the second things. Both of them are due on Saturday, but I haven't had a chance to talk about set 12.2 yet. The vectors, we haven't had a chance to talk about it. So I'm going to extend that homework past Saturday. Everybody understand? I don't think you're ready to do the homework yet. I want you to do it. And if you have done it, that's great. But I don't want to insist you do it yet because I haven't had a chance to help you. Anyway, what is on page 24 of the notes is, I said here, we're going to assume for a minute that we forget about coordinate systems, forget about axes and all that, and just sort of think intuitively about what's a vector. And I think people will tell you that vectors are a thing, some kind of thing that has length and direction. So the question is, if I start with that kind of vague definition, but I assume some things about geometry, like I assume 2 points determine a line. You can read through here. I don't know where my cursor went. You can read through here, 2 points determine a line. 3 distinct points will be called collinear if they all lie on the same line, and so on. And so if we assume some geometry, which you can read, I'm 18 after, I can't go through all this. And then I try to make line segments and try to denote some. So this, and make arrows. Those are directed line segments. So if we make up some arrows, this is what the book does in section 2, but he doesn't split hairs like I'm going to. So we're going to talk about line segments that are directed. And I say here, a vector is sometimes described as a quantity that has magnitude and direction. And I then give you 2 scenarios that physicists like to have. And the question is, how do we deal with these things? Well, it turns out that what we have is an equivalence relation, and that divides arrows, directed line segments, into equivalence classes like the wastebaskets I talked about earlier. But in this case, the wastebaskets are all full of arrows. If you picked up two arrows in the same wastebasket, you would notice that they have the same length and direction. Okay? It'd be like actually going to a store and buying two arrows that are from the same collection, the same color or something. They'd be the same length and the same direction. Now, the arrows you buy in a store don't have a direction, but when you shoot them, they make a direction. Okay, they go somewhere. Anyway, so on page 26, we talk about what a vector is. It's going to be an equivalence class where we say two vectors are related if they have the same length and direction. Two quantities are related. Okay. Then what I do is I define how you add them with only that description and how you lengthen them or shorten them. And so this is an attempt to take that vague description and make a mathematical definition. And so I go through several pages of what I want to try to do. And if you go through this, you're going to find out it's complicated because doing this is difficult to do. So by the time I get to page 30, I'm tired. And I've tried to do this really, and I've actually succeeded. If you actually make your way through this quagmire, you'll find out that I've actually got a system of adding and subtracting and lengthening and stretching and stuff vectors. But it's awkward. So I start over again. And what we're really going to do in here is deal with pages 31 on. So pages 24 to 31 was an attempt to build a system where I just try to go as far as I can with the concepts of same length and same direction without defining either one. That's what the book does. It never defines a direction. It never defines a length exactly. It just says we know what these are already. And we make up arrows from those two concepts. Well, I tried to make some mathematics out of it. It's very difficult. So what we do in math is we don't do it that way. We start over. And we spell out what we want our vectors to do. Okay? And that's what I'm doing here, spelling out two operations on vectors. And once we get the operations that we want, once we sort of put together the thing we want, then we define what a direction is and we define what a magnitude is, how long it is, each object. And then we have properties. So now, one more comment. We can spend a whole year on this, which we're not going to. It's called linear algebra. It's math 511 in here. We spend a semester on it here, but we have 2 semesters if you like. Anyway, it is a branch of mathematics. So there's a lot more in it than I'm going to say in 20 pages. Okay. But from page 31 to page 56 is when we talk about this new idea of defining what we want in the system and then trying to use it. And when we do this, we're going to be talking about the arrows, but we're going to be doing it abstractly. Anyway, I'm over time. It's 20 some after. Apologize for that. I got to stop the recording, which I'm going to do